Alright, today we're going to make our own personal dent in the universe by building up our intuition and understanding of fluid mechanics. Now, before I actually worked in the defense industry, I was actually an engineer in the gas and chemicals industry, and what I had to do on a daily basis is calculate the pressure drop within a pipe due to fluid flow, okay? This is formerly known as Poiseuille's law. Now, at that time, a lot of the engineers that I worked with, we would do this calculation in a program that was developed for us to put together any kind of fluid-based system we wanted, and then the program would do those calculations. Now, if you know me, I don't like trusting a program to do calculations for me, so naturally, I dug beneath the surface and tried to understand what was going on in terms of the physics, the math, and in essence, what the program was doing, okay? So what I found is that a lot of engineers surprisingly don't know how to do this, so I'm gonna help you avoid that mistake. I'm gonna make sure that you know the underlying physics and fluid mechanics that would allow you to derive or calculate a pressure drop in any kind of pipe with fluid flow, okay? Now, if you have not done fluid mechanics before, what's super interesting about fluid mechanics is the fact that unlike a lot of subdivisions of physics, the equation of motion actually does not have any kind of analytical solution. Yes, that's right. We have not officially derived a full solution to the equation of motion for fluid mechanics, which we know contains all the information we will need to derive the motion, the ensuing motion of any fluid-based system. So I know what you're thinking. Okay, we have this equation of motion. It's basically our map for dictating how to get to our solution. Well, if we can't use that map to get to solution, what in the world are we going to do? What are we going to do? So, what I'm going to state is that in any kind of fluid mechanics problem, solving a fluid mechanics problem is sort of like putting together a puzzle, right? How do we put together a puzzle? A puzzle has a ton of different pieces with information regarding the final picture, okay? And as we start dropping pieces down, we get a better glimpse of how that final picture is going to look like. Now, just like this in fluid mechanics, what we're going to find is that we have different tools and we can understand the problem in front of us and make a lot of different assumptions, and that's going to give us an additional set of information about our final solution. And every time we make an assumption or we solve one of our tools, we implement those tools, that's going to be analogous to dropping a piece of the puzzle, and we're going to see the final solution much better. For example, what tools do we have? Well, we have to assert conservation of mass, conservation of momentum, which gives rise to our equation of motion, the Navier-Stokes equation. That can give us some information about the final solution. However, we can have other assumptions. We could say, okay, there's going to be no slip at walls, right? We would expect fluid not to slip at walls. It's known as the no slip condition. We can assert that maybe the fluid is in steady state, that it's fully developed. These are ideas I'll talk about shortly, but after we assert all those things, right, it's going to give us a better picture of the final solution. And eventually, as we make sufficient assumptions and we use enough of our tools, we're going to drop little puzzle pieces together and we're going to have a clear glimpse of the final solution in such a way that it allows us to finally solve the equation of motion. In essence, what we're doing is we're simplifying that equation of motion, knocking out nonlinearities to the point such that we have a differential equation that we can solve. Okay, so that's going to be the name of the game. We're going to use that to derive a velocity profile for any kind of fluid, in particular an incompressible fluid, flowing through a pipe, and then we're going to use that to derive the pressure drop across any distance of that pipe. Okay, so let's jump straight into the problem. Before we do that, make sure you smash that like button. If you have not, please subscribe to our channel to stay up to date on any kind of videos or problems we solve for the future, and make sure you hit that notification bell. All right, let's jump into the problem. All right, so let's begin by actually reading the problem statement for this problem, for deriving Poiseuille flow. It states that from the gas or chemicals industry, we know that fluid flow through a pipe leads to a pressure drop. That pressure differential is responsible for generating the fluid flow and can be related to both the volume flow rate Q and the pipe geometry. Assuming that the fluid is incompressible and has reached steady state, key term, that's a puzzle piece we're going to use, derive this relationship, which is formerly known as Poiseuille's law. Now, what I've done is I've depicted the geometry we're going to use down here. Okay, so it's a pipe. It's basically a long cylinder of diameter d, and we have a radius big R. So we're going to do everything in the cylindrical coordinate system, and we're going to define R as the distance from the center line of this pipe, and x is going to be the distance along that pipe. You can replace this with z if you feel comfortable. Sometimes people use z here. We're going to use x in this case. And what we know is that if you have a pressure inside the pipe, and maybe let's assume this pipe is opening up to atmosphere. So we have atmospheric pressure over here at P2. On the left side of this pipe, assuming flow is to the right direction in the direction of x, okay, we know that P1 must be equal to P2 because P1 is going to be the force that is forcing this fluid through this pipe, okay? So we know that the pressure times an area is going to give us a force. If this is greater than the atmospheric pressure at P2, that's going to create flow. And this is sort of why I said the pressure differential is responsible for generating the fluid flow. So what we sort of think automatically is that fluid flow is going to be in the x direction, and provided that this pressure, this force, is greater than the force of gravity, we'd expect no motion in the r direction and also the theta direction. But we don't really know that quite yet. So we're going to have to use our tools and further assumptions, in essence, put these puzzle pieces together to see the final picture more clearly to sort of derive that result, okay? So what we're really interested in is the velocity profile that's going to occur, okay? So another thing I stated in the problem, I stated that this is going to be in steady state, okay? So all that means is, and I'm going to write that right here, steady state in my beautiful handwriting. That's a joke, by the way, if you didn't get that. So steady state, what that is telling us is that initially, our velocity is going to change, which I'll get to in a second. But basically it's saying that the derivative of our velocity v in terms of t, well, that's just going to be 0. It means that as time progresses, our velocity is not going to change. It's been fully developed, as I'll talk about in a second, okay? So that gives us a pretty good picture of this. It lets us know that we're going to have some kind of profile. Maybe it's parabolic, who knows? But I've drawn in here parabolic. It's going to look like that as such, regardless of time, okay? We're also stating that it's incompressible. So what does that mean? Incompressible. That's a fancy name, right? Incompressible. Well, as the name states, it's the opposite of being compressible. To compress, to make it smaller, to increase the pressure, increase the amount of mass that exists within a given volume. So that has to do with the density of our fluid. So if it's incompressible, that means we can't change the density of that fluid. So what we can assert is that the derivative of our density with respect to time is 0. In other words, it's constant. What kind of fluids do we know that do that? Some fluids that do that are water, for example. So what we know about water is it's incompressible. And in particular, when we're trying to do tests, trying to test the structural integrity of pressure vessels, for example, we're going to want to do that with an incompressible fluid like water, so that when we put all that pressure into that vessel to see if it bursts or not, if it does burst, it's not going to create a catastrophic event where it's sort of like a bomb. You could do pneumatic testing where you pump in air, but that air, it's actually compressible, so it can turn a pressure vessel into a bomb very quickly, okay? So that's sort of a tip I've learned from the chemicals industry. But coming back to the problem, we see these guys right here. These are two simplifying assumptions we have. These are basically our puzzle pieces we're laying out so we can see the picture a bit better. It's still vague. It's not as clear as we want it to be. So the first thing you want to do in any kind of fluid mechanics problem is you want to do what we have here for our first bullet point. I'll put a little bullet right there. First, we must assert conservation of mass using the continuity equation for incompressible fluids, okay? So that's a big one. It's incompressible fluids right here. I'm going to underline that. And what you find in the fluid mechanics course, the continuity equation is just, it's a certain conservation of mass. What I'm saying is that any mass that comes into this tube on the left-hand side must equal to the mass that flows out of the tube on the right-hand side. Now, when it's incompressible, our density terms cancel out, and we get this. Basically states the divergence of our velocity profile is equal to 0. In essence, that means that, right, there's no divergence. It's not spreading out, in essence. And that makes sense because within this, the mass can't move out, it can't move in, it can't build up, okay? Our mass is constant. So when we take this and we apply it in cylindrical coordinates, the math gets sort of convoluted. We get this huge statement here, which states 1 over r times the partial derivative with respect to r of r times the velocity, the r component of the velocity, plus 1 over r times the partial with respect to theta of the theta component of velocity, plus the partial with respect to x of our velocity component in the x. Now, all this is equal to 0. And I know what you're thinking. You look at this equation here and you're like, whoa, well, I can't make much headway. I don't know what exactly I can do with this. How can I charge forward with this? So what you're going to do is you're going to want to make more simplifying assumptions. In essence, we need to find additional puzzle pieces that we can slip into our puzzle so that the problem looks clearer, so we can see the final solution more easily, okay? So I'm going to talk about 2 puzzle pieces we're going to place right now. The first one has to do with the pictures I have down here. And I'm going to dive into some fluid mechanics theory and help you understand what happens when fluid flows over other objects. So on the left right here, I have what happens if you have fluid flow at a velocity u naught that's flowing into a plate. So the plate is down here. It starts at x equals 0. What happens? Well, we know that all objects experience friction. So you want to think about like your hand moving over your other hand. You can feel the resistance. It wants to push it back. As we learned in Physics 101, you have a force in the opposite direction of your motion. So with fluid, it's no different. And what we state is that there's a no slip condition, which states that fluid that's moving across an object, the fluid at that object has to equal 0. So if you have fluid that flows in right down here, and it's trying to move in this direction, right? You have a pressure gradient that's pushing it, but it can't move on that surface. What is going to happen is that those frictional effects, it's going to build up, okay? It's going to build up. So right here, you might have no motion. Then that no motion is going to affect the fluid up here, but it's not a solid object, so the frictional effect is not going to be as much, right? So it's going to build up, and over time, you get what is known as a boundary layer, okay? So the fluid, you might get some vorticity, where the fluid, due to that friction, it's going to want to move in a circular fashion. But eventually, you get this boundary layer that's building up due to the viscous effects, right? It's going to build up, and that boundary layer is going to increase, where the velocity is slowing down, okay? Farther away from the plate, it's not affected. Now, if we take this idea sort of in a Cartesian system and we wrap it around, so basically you're taking this plate and you're wrapping it around this whole tube, right? Because you can think of the edge of the pipe or the tube as sort of a flat plate that's revolving around some kind of center line. So when we do that, we have what we see on the picture on the right over here. So we're going to have, again, sort of like a velocity profile as such, where it's a constant velocity in the r direction. So it's going to flow in, and then along the edges, all around this pipe, the viscous effects and friction are going to build up. So that's going to slow down the motion close to the walls. And as time progresses, as it flows through this pipe, it's going to build up. And you see right here that that boundary layer is going to start increasing. And as a result, our velocity, which was constant initially, it's going to slow down. It's going to slow down until we get to 0 at that wall. The viscous effects are going to penetrate into our velocity profile. So as that boundary layer builds up, you're going to see it slows down more and more. So you can see this at a subsequent time until eventually the boundary layers are going to meet up, right? That's due to the geometry of our pipe. So when those boundary layers actually build up and build up, what you're going to find is that you would expect some kind of parabolic velocity profile. And that's why we sort of have that here, sort of hinting at where a final solution should be. But eventually, you're going to get this velocity profile. And once it meets up and it stops changing with time, you have what is known as a fully developed velocity profile. Okay, fully developed velocity profile. Okay, and as a result of that, what does that tell us? So if it's fully developed, how do you think it's going to look further down the pipe as x increases? Is it going to change? Think about that a bit. Is it going to change if the viscous effects have built up, the boundary layers have met together, and, you know, there's hardly any room for change, right? So as a result of that, right, it's not going to change as it moves down. It's fully developed. So one puzzle piece we can get from studying this idea of the boundary layer is we can assert that the partial of the velocity profile in the x direction with time, or actually, let me back that up. Let's see how it changes in the x direction. This guy is going to be 0, okay? It's not going to change. It's not going to change. So this is another puzzle piece because it allows us to see what's going on here clearer. Like, as a result of talking about steady state, incompressible flow being fully developed, we sort of generated what this velocity profile is going to look like. So you can see putting those puzzle pieces together gave us a clearer picture of the final velocity profile, okay? And furthermore, using this, we can take our tool, which is another puzzle piece, and we can say, whoa, look at this guy here. This allows us to say, well, this is 0, but we still can't really get anything valuable out of this. Now, based upon what I said previously, that the pressure is just in the x direction, and we would expect the velocity profile to be in the x direction, we would expect velocity not to be in the r direction. And we would also expect that if we neglect the effects of gravity, as we rotate around here, the velocity profile is not going to change. It's not going to change. So that gives us something which is known as an axisymmetric profile, right? And that allows us to assert, if I change back to black, that the partial of the velocity component in the theta direction, actually, give me a second, let me get that back. This guy equals 0 because why? Why is that? This is the axisymmetric property. This is true because as we move along here, right, it can't change. This guy we're asserting is just constant. It's not changing. So the derivative has to be 0, right? So when we get that, that helps us feel better about this parabolic shape. We assume it's going to rotate around. It's going to be axisymmetric. We're starting to see the full picture of our velocity profile. And furthermore, we can come up here and we can say, oh, well, wait a minute. This guy it's just 0. And we see that our assumptions are driving the problem forward solely because we can't solve that equation of motion. There is no analytical solution. So once we get this, what we can say is that we can use this guy right here. And in essence, all we have is that, you know, the derivative of r, VR, with respect to r, is equal to 0. So this tells us that in the r direction, VR is a constant. This guy is a constant, okay? So we can make a further assumptions about this. Now, what we know is that, let's see. So V sub r must equal to 0. Why? This is the no-slip condition. It's basically saying that at the boundary, it can't move due to the no-slip. That's what we talked about with the boundary condition and how viscous effects build up. But because of this, and because this has to be constant, if the velocity profile equals 0 up here, and it's a constant, it's not changing with respect to r, then we can assume that C, right? This guy must, it has to. This guy, VR, must equal 0, okay? So that's the dent in the universe we've made so far. This is another puzzle piece we're going to use. So this guy, we get that VR equals 0, thanks to the no-slip condition, okay? And that's basically the information we obtained from the continuity equation. So by asserting that conservation of mass holds, this tells us that there's no velocity in the r direction. We found there's no velocity in the theta direction. We know that it's all in the x direction. So everything we've asserted so far are simplifying assumptions essentially allow us to assert or get a better picture of what this is going to look like, and that's going to help significantly when we take a look at our equation of motion. Let's do that next. All right, as just stated, now we got to take a look at our equation of motion, which is obtained from conservation of momentum. So the first bullet point here states that next we assert conservation of momentum using the Navier-Stokes equation. That's the big guy we're going to use for each separate coordinate. So the Navier-Stokes equation comes into play. It's basically the conservation of momentum. It comes into play with incompressible fluids and also Newtonian fluids. And in essence, what we're trying to do is we're trying to apply F equals ma to a fluid. But with a fluid, a fluid does not have a definite shape, right? The volume is not set in stone. It's not a solid. So the mass may be controlled, but that mass can take on any kind of volume, any kind of shape. So we need to apply conservation of momentum, or F equals ma, to a fixed space, what we're going to call a control volume. And when we do that, we end up with the following equation, which is known as the Navier-Stokes equation. Now I'm going to break down the different terms in here so you get sort of a physical understanding of this, but the main intent of this video isn't to derive the Navier-Stokes equation. I'm assuming that you have looked at this before, so we're going to proceed as such. Okay, so you look at this and it's pretty convoluted, right? A lot of vectors, a lot of, gradients and divergence, and we have Laplacians. And as I stated previously, there is no set solution to this. I can't solve it. You can't solve it. Woo! So what in the world are we doing here? Well, there is no analytical solution, but what we're doing is we're putting all these puzzle pieces together to try and get a clearer picture and simplify this equation such that we can solve it, right? That's the name of the game, and that's why we've been putting together all these puzzle pieces, okay? So first and foremost, what this states is that the density rho is multiplied by dv dt. So this is sort of the acceleration component. It's our time component, and you can tell this is just A. This is basically ma. It's ma divided by volume, okay? Right? Because we're doing this per volume basis, okay? So we have sort of a time component on the left side here. And then we have plus v dotted into the gradient of v. So what is this? This is sort of a convective term. What in the world does that mean? Well, this is, in essence, the flow of momentum across the boundary of our fixed control volume. In essence, what we're saying is that momentum can flow out of or inside this control volume, so we need to account for it within our balance, our conservation of momentum. So all of this is set equal to rho g, our external force, our external body force, minus our gradient p, and that's the change in pressure as noted here from P1 and P2. And what gets added to that is the viscous terms mu, the viscosity, times the Laplacian of v, okay? So in essence, we're just doing some of the forces on a cube, a volume cube, small infinitesimal cube of space. We're trying to control that volume, and we get this convoluted equation here. So what you do in fluid mechanics is you need to break this down into each individual component. We're going to have an r component, a theta component, and an x component. And what I've decided to do, we're going to take a look at r first, and I've pulled the exact values from the textbook, and as you can see, Initially, this vectorial form is convoluted already, but when we jump into the individual components, we get a ton of, this is very, very hard to solve. Nobody knows how to solve this. There is no analytical solution to this, okay? So I want to make note that the textbook I chose to use changed our X to a Z. So you're going to see VZ and DDZ in here, but that's actually X in terms of here. So you can use whatever variable you want. I chose X. The textbook I looked at used a Z. I just want to make that note so you guys aren't confused. But in order to make some headway with this equation, what we need to do is, what's the name of the game? We're going to take our puzzle pieces, fit them together, and that's going to give us a clearer picture of what's going on. And that's going to simplify this equation into a form that we can solve, okay? So first and foremost, this is a lot of stuff going on here. I'm going to color code this so you can sort of see what each component is. So here we have sort of a time component. This is the time component shown above. Then we have our convective terms. A lot of convective terms, right? We got the gradient and we got to take our dot product. So we have to basically have terms for each component, right? Here's our R, our theta, our Z. So these guys are as follows. And then we have our body forces or external forces. So we have our body force here. We have our pressure force right there. I'm going to highlight that. And then just our viscous terms. Last, again, it's Laplacian. So we're going to have three components pretty much. Our R, our theta, and our Z. And you can tell this is a very convoluted equation of motion, okay? So those are all our terms that pop out of this vectorial form. And what we're going to do is we're going to apply the method I just talked about. We're going to use our puzzle pieces to simplify this equation, okay? So one of our puzzle pieces states that this is in steady state. The velocity profile is not changing as time progresses. So using that, we just pop this guy off. That is 0. We found from our continuity equation that there is no velocity in the R direction, and we can sort of insinuate that based upon what we know, our physical understanding of the problem. So all this becomes 0. Next, we have a V theta term. It's axisymmetric, so because of that, right, this guy becomes 0. So on and so forth. We have another V theta term. This guy becomes 0. So you see, we're dropping out a lot of terms. We're really simplifying this equation, and you can see the power of the method of putting these puzzle pieces together to simplify the equation. So next, we have a VR, right? If VR is 0, it doesn't matter if we take a derivative with respect to x, in this case, in our problem. This guy is 0. Next, we have our body force, rho gr. As I stated in the problem, our pressure term is going to be much greater than our body force. So this is basically insignificant in terms of what we're taking a look at. We're going to neglect gravity. It's not going to have any effect. This guy is 0. Our pressure gradient is going to be retained. That guy is going to stay. And then all we need to do is take a look at our viscous terms. So we know down here, again, our puzzle piece says that VR is 0. All this turns to 0. We have, again, VR is 0. We know that we have an axisymmetric profile, dv theta, d theta. That's just 0. And finally, VR is equal to 0. So this guy pops off to 0. So you're probably like, whoa, wait a second. That's a super convoluted equation. And we drastically simplified this. This is the power of using our puzzle pieces, okay? It's a very, very powerful approach, and it allows the problem to be tractable. So what did we just find? We just found that the pressure gradient, or dp/dr, this guy is equal to 0. Well, what does that tell us? This tells us that pressure is not a function of the variable r. Okay? And that's a big assertion. So we've increased the size of the dent we made in the universe. We're going to highlight this baby in Galaxy Ink. We get that guy. That's good. And the name of the game in fluid mechanics is you make these simplifying assumptions to your equation of motion until it's tractable, until you can solve it. So you're going to do this a lot in fluid mechanics. Another thing you're going to do is you got to really define this pressure gradient, because if you don't know it, you don't have a formed for that pressure, it's going to be hard to solve your problem. So we got one puzzle piece here in regards to that. Next, what we need to do is we have to consider the next component. That next component is going to be theta. So let's jump into it. Okay, so I've pulled that next component, that next theta component. So this is the theta component of this vectorial form of the Navier-Stokes equation right down here. And again, I've highlighted the different terms that are present in this huge expression. Okay, we have time components, convective terms, external body forces, and viscous terms that appear in our equation. Now, what we're going to do, again, we're just going to use our puzzle pieces, start placing them together until we get a good vision in terms of what this tool can provide for us, what it can actually do for us. So if we pull out our red ink right there, and we first start at the left side of this equation, we know that we have steady state, so it is not time dependent. So this guy is going to cross off. It's going to be 0. We found that VR is 0, so this whole term is going to be 0. And again, you're going to see a lot of zeros popping up, at least for the r and theta terms, okay? Because we know the velocity is probably, well, we see right here that the velocity is going to be in the x direction. And again, this z should be, this z should be in x, okay? So proceeding, we know one puzzle piece tells us that v theta equals 0. So this guy cancels off. We get a 0 right there. The next term, both of these guys are 0, so that has to be 0. V theta is 0, so that becomes 0. Okay, moving to the right side of the equation, we know gravity is negligible. This guy becomes 0. We have to retain our pressure gradient because this is a real physical phenomena at play in our problem. And then we jump into the viscous terms. We know that v theta is 0. This whole thing drops off to 0. V theta again is 0. That's another 0. VR is 0. That's a 0. And v theta is 0. So that becomes 0. Okay. So this nice big scary equation reduced down to something that's nice and solvable. What did we actually find from this component of the Navier-Stokes equation? We find that, well, we get 1 over r, negative 1 over r, dp d theta is equal to 0. And that tells us that we could just multiply by r, multiply by negative 1, and in essence, we just get that dp d theta equals 0. So, you know, it doesn't seem like it's a big gain, but in essence, what this tells us is that, again, pressure, we know that pressure is not a function of r. Now we know that pressure is not a function of what? Of what? Theta, right? It's not a function of theta. So this tells us that our pressure gradient must be either a function of r or a constant, okay? So that initial dent we made into the universe, it's getting bigger, it's getting bigger. So to signify that, we want to box this in with our galaxy ink. And that's the result we get from this equation. Next, we're going to move on to the most important component of the Navier-Stokes equation, which is the x component. This is going to get our simplified equation of motion that we're going to have to solve in order to figure out the velocity profile of this fluid motion. So last but certainly not least, here's the x component of the Navier-Stokes equation. Again, I've highlighted all the different components that are coming out of this vectorial form. And what we're going to do is we're going to employ the magic of our puzzle pieces. Again, we want to see a clearer picture of how this is going to look. So first and foremost, we look at the time component. We know it's in steady state. This guy has to disappear. This guy is going to be 0. Next, the next term in the convective term. The VR term is 0. We know VR is 0, so this guy cancels out. And before we proceed, I want to make another note. Remember, the textbook put a z. You can put any variable you want. This is talking about the variable along the center line of the pipe. We use x in this case. The textbook used z. Please do not let that confuse you. Okay, proceeding. Next, we see we have a v theta, but we know v theta is 0. There's no velocity in the theta direction. So this guy is 0. And then next we have dvx dx. Okay, what is that? Well, we know that the velocity profile is fully developed, so we can use this guy. So this becomes 0 also. It's starting to look like everything's zero again. Or is it? Let's proceed to the right side of the equation. So we're neglecting the body force, the gravity. This guy is 0. And then we're going to retain our pressure gradient due to P1 and P2. And in the viscous terms, we see here that dVx, well, Vx is not 0. With respect to R, okay, so we're getting something. We're going to have this big, huge component here. This is going to exist in our equation of motion. We're going to retain that. Next, we get this guy. Well, we reason that velocity is not going to change in the theta direction. That's an axisymmetric property for v theta. Well, this actually extends to all velocity components. So this guy is going to be 0 due to the axisymmetric property. And then finally, we have dvx dx. Okay, again, I'm changing the z to an x. We know we're fully developed, so this guy has to equal 0. And there you have it. We have something that looks like we can use it as a equation of motion. Okay, so what we're going to do is we're going to start pulling this stuff together. We're going to pull our dp dx on the left side right here. So I'm going to write that down. And I'm using red ink. I do not want to use that. I'm going to switch to black really fast. So we're going to write down dp dx. We get this guy. dp dx is equal to, so I just brought this guy over to the left. This is equal to mu over r ddr of r times dvx dr. Okay? So, it doesn't look pretty. But in essence, we have something that we can actually work with here, right? So what I'm going to do is I'm going to pull the r and the mu on the left side, and then we're going to see if we can do anything about this. So we're going to have a 1 over mu dp dx times r, and that is equal to ddr r dv x dr. Okay? So this guy becomes our new equation of motion. That dent in the universe is getting bigger. Let's make note of that. We're going to highlight this guy. This becomes our main equation of motion we're trying to solve. And if you look at this, you know, it's not too bad. It's not too bad. We can actually solve this. And that's what we're going to do next. Let's jump into it. All right, so at this point, we have this nice equation of motion here. We could probably solve this, but what we need to do is we need to massage it a bit more. So using our puzzle pieces, this gave us a clearer picture of the final motion that's going to ensue, but it's, you know, there are some missing puzzle pieces. We need to fill in those details in order to see the full picture. And I know exactly what you're thinking, right? The previous equations were super convoluted, but you look at this and you're like, whoa, well, how the hell do I solve this? In particular, this dp dx looks very disconcerting, right? This is very challenging. What do we put in for this? What function does it have? And as I mentioned previously, a huge part of fluid mechanics is figuring out what the pressure function actually is so you can proceed, you can solve this. And the way in which we're going to do this is I'm going to make certain assumptions, okay? I'm going to use some of these puzzle pieces to make it a bit clearer, okay? The reason we're going to use is as follows. This is mathematical reasoning, mathematical deduction. So we're going to say that, okay, we know P is not a function of theta and r from this. So at most, it could be a function of x. Okay, it could be a function of x. But we see here, this Vx could be a function of r. So do you see the dilemma that's illustrated by using these puzzle pieces? Well, on the right side, if r changes and v changes because of that on this side of the equation, this guy cannot change because it's not a function of r, so that would break the equivalence. Do you see that? So, for example, let's say we're considering the velocity at this r component here, which we can see is different due to viscous effects, we expect u to be a function of r. If that changes at this point, right, well, this guy can't change to compensate for it, so this no longer holds, and in essence, we violate conservation of momentum, which is, that's a no-no, that's bad, we don't want to do that. So, because this guy cannot, right, it cannot be a function of r, right? It cannot be a function of x either, okay? So in essence, what we're going to say, because if this is a function of x and x changes, this could change, but maybe this is not a function of x. Well, indeed, it's not a function of x because it's fully developed. So then that would break this equivalence also. So because of those things, what we're going to assert, and I'm going to write that right up here, we're going to assert that P is a constant, okay? P is a constant, right? It can only be a constant value. And by that, what I mean is like it could be 10, 5, 3, 2, or 1, okay? So this guy right here, all this becomes is the gradient. The gradient is just delta. It's just P2 minus P1, okay? So what we're going to get is this guy just becomes delta P. So we get delta P right there. And then we're going to move the R over here. We're going to get 1 over mu, just like we did on the right side over here. We're going to move this R over there. And then that gives us our DDR of R dVx dr. Okay? So to proceed further, I'm going to back up a little bit. And we know that this guy is a constant, but I would technically have to put a length under here. I'm going to do that later. So what I'm going to do is I'm going to get rid of this, and we are going to redefine it, our pressure gradient. We're going to simplify our life a little bit. I'm just going to leave it as a dp dx, but we know this is sort of like a numerical value, so it becomes sort of like a constant in essence, okay? So this guy is going to be left as such, and all we have to do now is, what are we going to do? We are going to integrate on both sides. So we're going to multiply the dr over. We're going to get a 1 over mu. We're going to pull out that constant along with the dp dx. Okay? And we're going to integrate with our r over there, dr. And that is going to be equal, well, when we integrate in terms of dr, this just becomes r dvx dr, okay? Well, this integration is pretty easy, right? You could do this. We could do this, right? We got this. So we write down our constants, 1 over mu dp dx for our next step. And the integral of r, well, that's easy. That's r squared over 2, right? So that's just r squared over 2. Okay? And then we get that guy. And then we have to add a constant on, right? So I'm going to add constant C1. And that is all equal to R dVx dr. All right, so the next thing we need to do, we need to get rid of this R, and then we have to integrate again, yet again. So when we do that, we divide by R, we get 1 over mu dp dx R over 2 plus C1 over R. Okay? Now, what I'm going to do is, I'm just checking to see if I have some board space. We do. I'm just going to integrate on both sides with respect to dr. Okay, so I'm going to write that dr in here. And we are going to integrate yet again. And when we do that, that gives us our Vx function, okay? So surely we can do this integration, right? This is not too difficult. So when we do this, we get a 1 over mu dp dx. The integral of r over 2 is going to be r squared over 4. And then we just have to integrate the next one, which is just the integral of 1 over r is the natural log, right? That's just C1 ln of r. And then we have to add a constant, c2. All right, and then that's all equal to Vx. Okay, so next, what we need to do is, we got this nice general form of the equation, and like I like to say, differential equations are sort of like erecting a building, right? It forms the scaffold of how it's going to look, and we have to fill in the details. Well, we have this nice scaffold here, where we have the general form of the equation. Now we have to fill in the details of this guy. In essence, it's sort of like building that puzzle, right? We're getting closer and closer. Our vision of the final velocity profile is brighter. It's more clear. And next, all we have to do is solve for these guys. And how do we do that? We do that by using our boundary conditions. So, to make headway in solving for C1 and C2, the first boundary condition we're going to use is boundary condition 1, which asserts that we know there must be finite velocity values, right? So if we look at the velocity profile and what we talked about in terms of the viscous terms building up in the boundary layer, we knew that initially there was some velocity flowing in, then at the entry portion entering into this pipe, right? That velocity profile slowed down close to the wall, and we had some kind of maximum value right here, right at the center line of the pipe. So we know that that cannot be infinity, right? That doesn't even make sense. Infinity terms should not pop up in our physical surroundings. So what we're going to assert is that if we look at this, when r is equal to 0, we get an ln 0. Well, that would give us a negative infinity, right? Because e to the negative infinity gives us that 0. So what we're going to assert is that because we want finite values, because we want this to converge upon reality, we have to assert that C1, the constant C1, must equal 0, okay? So that is the first boundary condition that we apply. So we get that guy right there. And next, what we want to consider is boundary condition 2. So as I write that up, you can think about it. What do we know? Well, the other boundary we have is when r is equal to capital R, and I sort of talked about that already, right? Earlier in the video, I said there's a no-slip condition. In other words, that fluid across a solid barrier cannot move due to friction. Now, whether or not that is true experimentally is another question that perhaps I can make a video on. If you want to see that, drop a comment in the comment box below. But what we know is that Vx, when r is equal to big R, we know that that velocity must equal to 0. And that's partially responsible for the boundary layer that builds up and for slowing down this velocity up to the center line of our pipe, okay? So if we exert this, we assert that C1 is 0, and we're going to say, let's write it up. Let's write this baby up. So Vx sub 0, not sub 0, sub R, big R, is going to be equal to, I'm going to pull the dp dx out front, dp dx, and then we're going to have big R squared over 4 mu, okay, plus C2, and we know that is all equal to 0. So when we take this term over to the right-hand side, we find that C2 is equal to negative dp dx r squared over 4 mu. Okay? So that is the last boundary condition and the last constant we needed to find. We're going to highlight that baby because that baby is important. And what we could do is, in essence, I'm going to check the board space I have that is available. So it looks like I do have some room on the bottom right here. What we could do is we could just plug this in and see what we end up with. So we see that it's going to be sort of like an r squared minus another term. And we're going to have the same constants out here. So if we use this as a reference, we're going to come down right here, and I'm going to pull the constants out right out in front. So we're going to have a dp dx. And I'm just going to make a quick check. Yup, it looks like we have good space going on here. So we're going to have a 1 over 4 mu. And all of that is going to be multiplied by r squared minus big R squared. Okay? So this guy is going to be our velocity in the x, and it is going to be, as you can tell, a function of r. Okay, so that's the guy we have. That's a very important equation. I'm going to highlight that. We made a huge, huge dent in the universe. We figured out exactly how this is going to behave. That's a big, big win. Next, what we're going to do, we're going to try and interpret this, and then we're going to try and figure out how we can use this to determine the volume flow rate that we're going to need to relate our pressure gradient to Q, our volume flow rate. Stay tuned. Okay, so first, to better understand what's going on here, I have plotted up the velocity profile right here, but we have to massage this equation a bit to get it into this form in order to qualitatively understand what is going on. So initially, when we were running through this, I started defining what this pressure gradient dpdx was defined as, and started getting it started getting tricky, so I wanted to save it for later. What we want to do is, we know that dpdx is a constant, so we're going to literally put it down for what it is, given this figure, given what we have, the information we have. So we know that in x, this is the x direction, the change in pressure is no different than P2. So we get P2 minus P1, and that's over the length of the tube or the pipe we're considering. So in this case, we're just going to have a constant L value here, and then we have everything that goes as follows. And I'll explain why it's not as straightforward as you'd think shortly. So we write down that guy. This is all equal to Vx sub r. Okay, so we have this, and my question for you is, what is P2 minus P1? Well, in order to create fluid flow in the x direction, we know that P1 must be greater than P2. We talked about this in the beginning of this problem, right? So if P1 is greater than P2, we know this guy is going to be negative. So what we can do is, we can get our pressure drop, where we're putting that negative value within our terms. We could define it as delta P, and we can just say, well, this is delta P. This is delta P over 4 mu L times the following. We can put this negative value, we can multiply everything by negative value, right? Because we know this is negative in and of itself, and get big R squared minus little r squared. Set all this equal to Vx sub r. Okay, where we have to define delta P as the inverse, P1 minus P2. Okay, so if we put this guy in and we multiply by a negative sign, we would get this back to P2 minus P1. That would be reversed back to what we wanted, and then we would have the equation that we want. Okay, so this is the final equation we're going to use shortly to figure out volume flow rate. Again, this is the major dent we had in the universe, so that deserves Galaxy ink. We're going to highlight that baby. We got that. And now we're going to jump over to our graph that we have right here. So what this is telling us is that when R is equal to positive big R, basically the radius of the pipe up here or the radius down here, so positive or negative big R, Vx equals 0. And we see that qualitatively here in our plot. This is basically the enforcement of the no-slip condition. And we find that the viscous terms slowly make it retards the velocity close to the wall. So these values are lower than what is in the center line of the pipe at 0, right here. So right here. So here we're going to have a max value that I noted right here. We're going to have some max value right up there. I'm going to put that there. And we're going to do this. Let's use a red ink. So this guy comes all the way up here. We're going to call this U max. That's our max value. And this is going to be no different than delta P over 4 mu times L times R squared, capital R squared. So we get some maximum value that's out here. I chose arbitrary values for this plot, but you can see that basically what this is telling us, what all this information told us, putting the puzzle pieces together, finally we see the clear picture. This is the full picture right here. This is our puzzle piece in place, right? You can think of these little grids as the little puzzles we had to put together. And it just tells us that it's a parabolic velocity profile. In the center, we have this maximum value out here when R is equal to 0. And we're going to use this, in essence, to figure out the volume flow rate that is flowing through this guy, okay? So we're going to need to do that to relate this delta P, P1 minus P2, to our volume flow rate and also the geometry of our pipe, okay? So let's do that next. Okay, so compared to what we've done previously working with the Navier-Stokes equation, calculating the volume flow rate is very easy, right? This is child's play. So we know that the volume flow rate is the velocity flowing over the area of the pipe. And this is looking straight at the pipe where the radius goes out all the way as such. So all we need to do is we just have to take our velocity profile and multiply it by, or rather integrate over this area. We want to add up all the velocity components going through this area right here, right? And when we hear add up all those infinitesimal amounts, what is that a trigger word for? Calculus, for the integral, right? So what we're going to find is that Q, our volume flow rate, it would help if I had the black pen available, but Q, sorry about that, Q is equal to the integral of our velocity profile in the x direction, dA, okay? So dA, right? And we can further define that as such. So what we need to do is we need to integrate in the theta direction and also the r direction. So if I blow this guy up and take a little slice right here, we're going to have sort of like a guy that looks sort of like this, if you haven't seen this in calculus before. And what we know is this distance here, right there, this is r d theta. It sort of comes from r sine theta when theta is very small. I've explained this multiple times in my previous videos. And then here is going to be dr. So when we multiply the two together, you get the area of this little block here, and then you just want to add up around this entire area. So that's the name of the game that we're going to use. So we're going to integrate along r and along theta. So I'm going to plug in our trusty Vx equation right here. So we're going to have a delta P over 4 mu L times r squared minus little r squared. And here's the dA term that comes into play here. So we're going to have in r d theta. Back up a little bit. R d theta dr. Okay? So that's going to give us the entire area flowing through this. And we just need to set the limits of integration. So for r, obviously, we're going to go from 0 to big R for dr. And for theta, we're going to go from 0 to 2 pi, right? We want to go around this entire pipe, okay? And what we see right away is that, you know, there's no theta in here, so theta is pretty much a constant. We can take care of that guy pretty quickly right away. So we're going to do that first. We're going to pull out these constants here, and we know that there's no theta here, so we just get a theta, and we get 2 pi minus 0. So that's a 2 pi we're going to get on here. So we get a delta P. We're going to pull out the constants, we get delta P times pi over 2 mu L. And again, I got the 2 pi, that 2 divided by 4, that gives us the 2 on the bottom here. And those are the constants we get out in front. So all that's left really is just doing the integration on R. Okay, so this is big R squared minus little r squared dr. Okay, so this is the one that is a little difficult. It's still manageable, right? It's not that bad after working through the Navier-Stokes equation. So again, we're going to write up our constants, delta P pi over 2 UL. And then we get the following. So what we get is, oh, actually I forgot an R right in here. This guy that comes down right there. Sorry about that. So we're going to get big R squared, little r. So we're going to get a big R squared, little r squared over 2. That's the integration of R, the integral of R. And then we want to integrate this, basically R cubed. So we're going to get R to the 4th over 4, right? And all this is defined from big R to 0. Well, we know that 0 is just going to cancel out, so we can plug in the big R right away. And what we end up with is delta P pi over 2 mu L. And then I'm going to change this to parentheses. We're going to get R to the 4th, big R to the 4th, over 2 minus big R to the 4th over 4. So in order to make headway, what I'm going to do really fast, give me a second. All right, it looks like we do have some board space. I'm actually going to jump up here just to be safe. So we're going to have a Q, and that's going to be equal to, let's see. So we get R to the 4th over 2. So that's sort of like 2R to the 4th over 4 minus 1R to the 4th over 4. So that's 2 minus 1. We're going to get R to the 4th over 4. So in essence, we just get delta P pi R to the 4th divided by 8 mu L. All right, I'm going to check, make sure we got the right result. Yes, we did, because we're awesome. We're awesome. All right, so we got this beautiful result right here. Okay. This is the major dent we have in the universe. This guy is king. Right there. All right, so we get this guy. And what we want to do is we really want to use this to calculate our pressure differential, right? So we want our pressure drop, right? That's what we're trying to do as engineers, right? We're trying to figure out the pressure drop between point 1 and point 2. So what we can do is we can isolate that pressure drop, and we find the following. We get delta P is equal to 8 mu L times Q over pi to the pi times R to the 4th. Okay, so these are the final results we got. These are basically Poiseuille's law in all its glory. All right, so we got the results. We made a huge dent in the universe. Let's examine that dent and try to understand it a bit better next. Okay, so as I just said, we've made a huge, huge dent in the universe. Let's try and understand the implications it has. So this is Poiseuille's flow, basically the Hagen-Poiseuille law. Hagen was another individual who either contributed to it or was responsible for what was going on here. But this tells us a lot about the volume flow rate and the pressure drop. So first and foremost, When I was an engineer, if I used this equation, well, what I mean by when I was an engineer, when I was in the chemical industry as an engineer, I could have used this equation and I could have derived a pressure drop in any kind of pipe that I used for my designs pretty quickly using this, provided that it is laminar flow. And what engineers like to do is like to take this. You can take this and you can use it to determine the shear stress in your fluid. You can also determine something known as a friction factor, where we can experimentally determine the pressure loss. A lot of engineers do that. I prefer the analytical approach we used here. But you can use that for example, turbulent flow, where this no longer applies. What do I mean by turbulent flow? Turbulent flow is when the particles have so much energy that you don't have like a nice stream laminar flow of your particles, right? In laminar flow, it's sort of like sheets moving along each other, right? Everything's nice and orderly, and you sort of have streamlines as such. In turbulent flow, everything goes wherever the hell it wants. It's chaos in essence. So things get much more convoluted, and obviously we cannot use the same kind of analyses we just used. But if you use this guy, I've actually determined that this gives very accurate results in the field for determining a pressure drop. So that program I used, what it was doing was it was doing a calculation like this, depending upon the flow rate we had. There's something called a Reynolds number. I won't jump very much into that, but that determines the behavior of the different flow you have. But if that number is low enough, you're going to have laminar flow. And then this result will give you pretty accurate results. But this tells you a lot of information, right? So this tells you that if the geometry you're dealing with, if your pipe, if the radius increases, that factor, right, it's going to make your pressure drop much lower. So if you make the pipe smaller, thinner, your pressure drop is it's going to skyrocket. You're going to get a huge pressure drop. Okay. So you can see it has a huge effect. This R to the fourth, it's a very important term. Areas where this is used. What are some of those areas? So in the medical industry, they don't derive this equation, but they probably use this to explain to students a very important phenomenon, that this R to the fourth plays a huge role in what goes on. So what are people concerned about in the health industry? One thing is heart cancer, right? Not heart cancer, heart disease. So heart disease tends to happen when you get a lot of plaque along the artery walls right here. So you know, if this is your blood vessel, you can get a lot of plaque buildup here as such, and that can constrict the flow rate you have through your artery. In essence, that's reducing your big R here. It's reducing it down to something like that, for example. So that becomes your new big R. But if you decrease your radius, what does that tell you? What does this equation tell you? That tells you that your flow rate is going to decrease by a factor to the exponent of 4. That's huge. That is huge. So let's say you half this. You half it. Then your Q is going to basically go to, that's like 1 over 2 to the 4th. That's a lot. That's 2 times 2 times 2. So that's 4. That's 8 times 2. That's like 1 over 16, right? That's 1 over 16. So your flow rate is going to drop off quite a lot. Well, why is that a problem? That's problematic because you want a lot of blood to flow through your veins so you can get those nutrients to your organs that need it. So as you build up plaque and such, that's going to restrict the flow rate quite a lot. And that's why people end up getting heart attacks. That's why people end up getting a lot of health problems due to fat and buildup on their arteries, okay? So this is Poiseuille's flow. You can use it for pressure drops in pipes, for engineering. You can use it in the medical field, and it has a lot of important implications. That's why it's a law. That's why Poiseuille and Hagan are very famous physicists and scientists. But yeah, that's all I have for you today. So what do we do? What do we do? We use the Navier-Stokes equation, or rather, let's back up. We took conservation of mass, we took conservation of momentum, and then we used different simplifying assumptions, essentially puzzle pieces, to see the final picture more clearly. And in doing so, that allows us to simplify nonlinearities in our equation of motion, the Navier-Stokes equation, enough such that we could solve it, such that we could see the final puzzle complete. Okay? So this is the flow rate we can use for laminar flow. This is Poiseuille's law. I hope you enjoyed the video. If you have any questions, drop them in the comment box below. You can also send me any questions you have at ed@thekaizeneffect.com. I want to solve your problems for free. Yes, for free. So send me an email with your problems. I can get around to solving that, making a video, or potentially we can do live streams. Let me know what you want to do. I'm all open. I'm all open to any kind of idea you want. If you have not done so already, make sure you hit that like button, subscribe to our channel for future videos, and I look forward to working with you in future videos. Stay tuned. Hope you enjoyed the video.